Thank you very much. Especially probably make sure I have a clock. And okay. Well, I'm very glad to be here. As he said, I had a bit of a hard time. My plane was canceled this morning. Unfortunately, I had left a buffer of 4 hours, which I managed to use. Okay. So today I'm going to talk about technology, but I'm going to talk about technology from the point of view of biology, and I'm going to throw in some physics and mathematics along the way. This guy, well, I want to point out that technology co-evolved with early humans. I love this picture of the early guy, Stone Age man, skiing with his little hat and his pole and everything. And this is a debated point, but I strongly believe that tools co-evolved with our brain. Tools exist since 3.3 million years ago, being used by hominids. And these are the guys who were using those kind of tools back then. So they were very different than we are. And I would argue that the use of tools put a lot of evolutionary pressure on a certain kind of brain, and there was a co-evolutionary spiral. Without technology, none of us would exist. Now, what do I mean by this? Well, first of all, let me point out Malthus was wrong. It's quite clear that it's not just a matter of competing for a finite capacity of resources. In fact, there's been a coevolution of technology and population as we raise the carrying capacity of the Earth for humans from a very small number, probably 10,000 years ago, to a quite large number that we're feeling now. And by the way, the first person to make what seems to be an accurate estimate of where the human population is going to settle was von Leeuwenhoek, who did it by roughly computing the population density of Holland at the time and saying, well, that's about what I think the rest of the world could do. And he actually got it around 9 billion or 10 billion, which is about where we'll settle. But this coevolution was a very important thing, and Condorcet, unlike Malthus, actually in an essay that he wrote before Malthus, pointed out the correct mechanism, which is that we're continually expanding our technology. Our technology increases the carrying capacity of the world because it increases our ability to buy food. It makes our medical capabilities better, and the population grows, and then we have more inventors, and technology goes even faster. And in fact, it's not even clear. If you really literally didn't have tools, there are very few environments on the Earth where people could probably survive. I was influenced as a kid by Teilhard de Chardin, who I don't know how many of you know his work. He's a very odd fellow, a Jesuit priest who was a prominent physical anthropologist, most of whose work was not published in his lifetime because it was heretical. And he talks about the noosphere, which he defined as the intersection of the ecosphere, the biological ecosphere, human culture, and human artifacts. And he felt that these three things are all co-evolving together, and talks about the potential to have a hyper-intelligence, collective organism, and now then he becomes quite mystical, and I believe there was a mega point that we were teleologically being drawn toward. So I don't go along with that kind of idea. I think the logic's backwards, but I nonetheless think there's a lot is neglected in understanding the interaction between these things, and it's worth noting that much of our lives now is spent inside of an artificially constructed environment. We spend our time, we're in this building. We've got a computer here, we've got artificial light down on us, and probably most of you, like me, spend a lot of your day interacting through the internet in a strange kind of virtual world. And I argue that we don't understand the principles behind that world and what's driving the rapid change that we're seeing well enough. Now, there's a whole field of trying to understand technological change, which in this sense, it's very interesting, and the authors I'm writing here are some of my favorite authors, but it's strictly anecdotal. It's at the level of history. That is, I mean, history can be very insightful, but there are very few quantitative principles underlying the study. Let me say there's also economic historians, and there are economists, like growth economists like Paul Romer. I'll say a little bit about the kind of stylized theory they make. I would argue that the study of technology is pre-Linnean. That is, if you go back and read, say, a biography of Darwin, it's striking how much his thinking was influenced by what Linnaeus had done. Linnaeus provided the organization of the world that really structured the way Darwin thought, and in a very crude sense, I think you can argue that the Linnean taxonomy turned out to be a crude approximation of the phylogeny that Darwin says was effectively created through passage of time. Now, I want to argue here that technologies undergo Darwinian evolution in the sense that Darwin meant it. That is, they follow descent with variation and selection. There are a lot of details that are different. This is some points that we brought up in a review article that we wrote. There's also a very nice review article by Andreas Wagner and Rosen. So there are a lot of similarities between biological and technological evolution. They're both driven by selection. They both result in diversity. They both follow processes of incremental variation, temporal progression, and this may be a little more controversially, there's a purposeful function of the units. Of course, purposeful is always a tricky word. But there's a lot of differences. There's self-reproduction in biology versus artificial manufacture in economics. There's random variation versus conscious design, although some would argue that tinkering has a large element of random variation. In fact, Thomas Edison was famously quoted in saying something like, "Don't say I didn't make any progress, I just tried out 10,000 options that all turned out to be wrong." But actually, you know, then eventually he got it right. And you go back through what inventors actually do, there's an awful lot of just systematic or even random testing, random experimentation. Biological organisms are organized at a microscopic level. Human technology is organized at a macroscopic level, but that level is becoming increasingly microscopic through time as we, hit the nanoscale more or less now. Innovation in technology is more analogous to horizontal gene transfer. I think I have a slide here. That is, instead of the nice vertical evolutionary patterns you get from sexual reproduction, and that allowed Linnaeus to make a nice tree describing, giving a taxonomy of organisms, in technology, there's a lot of horizontal borrowing. While there may be a line of descent in a certain way, inventors borrow a little bit from over here and a little bit from over there. The web is much more tangled, and anyone who has tried to understand the taxonomy of bacteria is familiar with the much harder problems of taxonomic classification that you get when you have that kind of structure. The developmental process of technology is highly distributed. If you look at something like this laptop that I'm making now, we all know what an issue globalization is. Now this laptop was made in a distributed way throughout the world. And that's increasingly common of technologies. So, but I think the dividing line between these is going to become increasingly blurred. I'm sort of going along with various science fiction authors. Now, one important difference between the two is that the simplest technologies are far simpler than the simplest organisms. I mean, the simplest sort of self-contained organism might be a bacterium. A virus is no longer even self-contained. But it's still a far more complicated thing than the simplest piece of technology. I mean, technology could be something as simple as a rock. I mean, you read stories about animals, for example, taking shells from one place to another and using rocks to break them. So that rock is already becoming a tool, so it's a technology. So it shows you it's actually hard to even define what a technology is. Technology is more about a functionality than it is about a material thing, because that rock could either be just a rock or it could be a crushing tool. And so when one thinks about a taxonomy of technologies, you fall back on, in a sense, a much harder problem because you go back to something much more elemental, and you see that heredity, which is what biology focuses on with taxonomy, is probably not the most informative thing to think about. Somehow you can think about a specific functionality and how achieving those functionalities is changing through time, and you can classify simple machines into the kind of functions they perform. But it's not done. I mean, and I should warn you, I'm really giving a talk today about problems that are mostly unsolved, and I'm going to give you a little more of this big picture introduction, and then I'm going to plunge down into some very nitty-gritty things that will fall far short of the grand ambitions and big ideas that I'm talking about now, and then I'll come back up and surface a bit at the end. Now, another aspect of technology is that the data we have available is very different than the data we have available in biology. In biology, since before the time of Linnaeus, people have been collecting rich data sets on the world. It's been a huge effort in collecting fossils and classifying those fossils and mapping out our phylogeny. In contrast, there's no universally accepted concept of performance. I mean, we don't know whether we are in any sense better or worse than dinosaurs. It's a kind of silly question to even ask. In technology, in contrast, we don't have any kind of good taxonomy. The best taxonomies we have are those put together by the patent offices. And you can right away see that these are highly ad hoc by just comparing them. Different patent offices have different taxonomies. There's some convergence these days, actually. But when you look into those taxonomies, you can see that they're a curious mixture of functionality. What do the inventions do? Material, are they chemical, or what? So there's a whole class of chemistry that actually could perform chemical inventions that could perform many different functions that are overlapping with other things. And where do they come from? Because when there's a line of inventions, they often put them together, and they're put together largely just to make sense so that they know when a patent application is made which patent examiner to refer it to. But there's no good systematic classification for inventions, which means that when you start to do something more quantitative to get away from these anecdotal descriptions of the world, you're right away stuck with a feeling of inadequacy as you even try and track technological change, because it's not even clear what the right categories are. In contrast, and I'll talk about this today, there are certain lines of technology where there's a clear metric of performance and where we can track the way that metric of performance changes through time, and that actually leads us to some things that are very important to us as a society, and I'll get to that in a minute. Now, complexity economics approaches these questions from a bit different approach than standard economics. Standard economics assumes you have an aggregate production function. It was shown by Solow that technology is the main driver of growth, yet technology in a typical economic model is reduced to something like this. So this is a typical growth economics model. We have GDP over here, which is some factor A, which is called total factor productivity, multiplied by capital raised to some power, and labor raised to 1 minus that power. And technology is therefore this number. That represents technology, and technological progress is this number getting bigger. And what Solow showed is that if you look at the data on what's driving the growth of the economy in countries, and you look at things like capital investment and what's going on with labor, that, well, capital investment has some small role. Most of it actually goes over into this term. And then people like Paul Romer, who I mentioned already, actually may add some terms onto this function for things like intellectual capital, and we'll make this number a function of time and try and derive some equations for how that number changes in time. So I'm going to give you an example today where we actually think about this in a much richer way and try and get a better understanding of what's driving growth by understanding the structure behind that. So we need to get inside this black box, and I will give you an example today where viewing technology as an interacting and evolving ecology can give us insight into what's driving economic growth. Now, so I'm going to go over two examples. So we're now descending to the much more nitty-gritty level of this talk, where I'll first of all talk about trying to predict progress using just simple empirical methods, very crude. And then I'll introduce an ecological network approach to understanding economic growth and try and convince you that that actually gives some useful insight about what's driving growth. So to motivate this first part of my talk, I want you to look at this slide, which is plotting the cost for producing electricity on the y-axis against time measured, and you see the dates here on the x-axis, and we're looking at three different components of electricity generation. This line here is the price of coal, measured in units of the coal fuel price for electricity generation. In other words, to generate a kilowatt hour of electricity, it takes around a couple of US pennies of, per kilowatt hour of coal, and this is how that has changed through time. And when you look at that plot, I think that this is adjusted for inflation. The striking thing to me is that over 150 years, okay, there's some bumps in this plot, but it's pretty much a flat line. In fact, if you fit a statistical model to it, you get a random walk with no drift. And so coal fuel prices have made very little progress during that 150 years. At least they've co-moved with progress in the rest of society, such that when we adjust for inflation, we don't see any overall trend of reduction. In contrast, these red triangles here are the cost of generating nuclear power in the United States. There's a red triangle for each nuclear plant corresponding to the date where that nuclear plant came online and the cost of electricity that that nuclear plant generated. And what you can see is during the period where nuclear power was coming online, the cost has actually increased rather than decreased by a factor of 2 or 3. It's debated what's driven that. Certainly safety is a substantial factor. People got quite a bit more concerned about safety after 3 Mile Island and Chernobyl, and that drove the cost up. But it's not clear whether that's even the whole story. By the way, this red cross here is the cost of a proposed nuclear plant that will be built at Hinkley Point in Great Britain that would come online in about 2021. And this is the price that's been agreed on that the electricity would be supplied. It's kind of a joint Chinese, French, with a little bit of British venture. Now, in contrast, in these green dots, I'm showing you the price of photovoltaic solar energy. That is the cost of a module. I'm plotting it in different units because now it's in dollars per watt peak, meaning if you make a solar cell and you put it out in the sun, how much does it cost to make a solar cell that will generate that much electricity in the sun? And we've sort of aligned these axes to allow for the fact that, but between darkness and clouds, you maybe get a factor of 5 reduction in what you can actually get out of a solar cell on average. But we've roughly lined it up, trying to be, if anything, a little pessimistic. And this is what solar energy prices have done over the last 20 years. In fact, solar energy started, its first use was on the Vanguard satellite in 1956. The cost was about 3,000 times what it is now. And that actually happens to coincide with the first commercial nuclear reactor. So in that same period of time, one technology stayed flat or went up in price, another technology dropped by a factor of 3,000. So why is that difference there? That's a question nobody has a very good answer to, I would say. There's some nice work by Chris McGee at MIT that gives some hints, but I can't really answer that question for you. But what I can address is the question of, Do we think these trends are likely to continue based on what we know from looking at historical prices? And if so, how good is our prediction? And how does that affect the way we think about combating climate change? So I went backwards. Now, let me just point out that we've collected data on lots of technologies and looked at their trends through time. And most technologies are like coal or oil. That is, once you adjust for inflation, they sit around zero, which is maybe not so surprising because inflation actually already represents technological progress of the economy in general. But there's other technologies, some of which we're quite familiar with, like computers, that have been improving at roughly 40% per year. Remember, the economy as a whole improves maybe a couple of percent per year. So quite dramatic. And DNA sequencing, that depending on exactly what period and how you measure it, you get numbers between 40% per year and 100% per year. So some technologies are extreme outliers. This distribution, empirically, seems to be a highly skewed distribution with a few exceptional performers. And photovoltaics sit over here on this side of the tail. They're not one of the dramatic examples like computers, but they've been improving at around 10% per year over their history. Now, okay, so is this useful? Well, so let me just begin. One of the reasons I'm a physicist by training. Physicists are always attracted to empirical regularities. One of the most striking empirical regularities we have in this field is familiar to everybody, Moore's Law, which was postulated by Gordon Moore based on history he had seen up to that point in the manufacture of computer chips. And when he wrote his note pointing this out in 1965, which was, the original note was just about density of transistors in a silicon wafer manufacture. Interestingly, that spawned into a law about computer speed, about hard disks, which, think about that, that's actually quite a big generalization because while hard disks are used by computers, the technology is completely different. It's mechanical technology. Started out quite macroscopically and it's just been shrinking. And so there's been a sort of proliferation of variants of Moore's Law. And by the way, people often say, well, Moore's Law is just a self-reinforcing, it's just driven by self-reinforcing expectations. That's clearly not true because it wasn't stated until 1965 and it was based on empirical evidence of what had gone before 1965 when it was stated. And as I'll show you in a minute, lots of other technologies follow the same basic law. Now, a somewhat less familiar law was postulated by this fellow Theodore Paul Wright in 1936. It's a very interesting guy. His brothers, you biologists will be familiar with one of his brothers, Sewell Wright, one of the most famous evolutionary biologists. And I doubt there are any political scientists here, but Percival Wright, his other brother, is considered one of the founders of political science. He was the black sheep of the family. When World War I broke out, he enlisted in the Air Force, became a flying ace, came back and became involved in airplane manufacture, and in fact ended up heading the production of aircraft for the United States during World War II. But in 1936 he postulated a law which is that the cost of producing a given technology, like a specific kind of airplane, originally postulated this for airplanes, follows a power law. If X is the cumulative production of that airplane, he said minus alpha is a number around 0.3. That is, alpha is around 0.3. And so every time you double the cumulative production of an airplane, the cost to produce it drops by about 20%. And this law was actually used by Wright to successfully forecast what airplane manufacture was going to cost during World War II. And in the sort of business school literature, it's generated a substantial following. Now, just to show you how these two laws perform for representative technologies, transistors, photovoltaics, hard disk drives, and manufacture of ethanol, you can see the plots here for Moore's Law, where we plot the logarithm of the average unit price against time. we see the same technologies plotted in a different way against total cumulative production. So we plot the log of total cumulative production in number of units versus the log of the cost. And actually, as you stare at these, it's hard to say which is better. There's Moore's law, there's Wright's law. So that already is a bit puzzling. Now we resolved this by noting that actually, if you also look at production versus time, for these same four technologies, or for lots of other technologies, production tends to go up exponentially too. And at least for technologies that are undergoing the kind of rapid improvement that we're talking about here. This doesn't apply to technologies that are improving. And you can actually see how these laws can coexist if you have cumulative production growing as some exponential in time and cost dropping as some exponential in time. Just eliminate time and now plot cost as a function of cumulative production, then you get a power law, and the ratio of exponents of those rates become Wright's law. So this calls into question, well, and so we tested this in this paper whose lead author was Bioscience, and you can see that if you take either approach, you essentially get all the data clustering along the identity line. Leaving the question about what's really going on. Does it just happen that production's going up exponentially and costs are dropping exponentially and it's just kind of a coincidence? Or is it really the case, as people postulate for Wright's law, that there's some kind of learning process so that as more and more of the technology is produced, people spend more and more effort trying to improve it, and those improvements get embedded in the technology and the production process, and that's what's going on. Or is it something like an economy of scale? And you can find data, I have to say, supporting all of these hypotheses. And I think that actually may be the correct answer, that it's some combination of all of those factors. We would love to tease out better what those factors are. Now, let me just mention, I don't know, I always feel a little bizarre mentioning this, but my postdoc, Bela Naj, became, we originally noticed this, and then we realized this fellow Sahal had actually said this in 1987, pointed out that this would be true. And then my postdoc, Bela Naj, actually realized that Sahal had just disappeared. It's one of these cases like Majorana, where just poof, he wasn't there, and nobody knows, you know, there was no body was found, he just disappeared. And about 2 years after that, my postdoc Bela Naj just disappeared. So it's a strange thing. Maybe it's a dangerous field. Now, I began by asking you, is technological progress predictable? The answer is going to be yes, but I want to say forecasts without error bars are useless. That is, people, we are not the first to try and use Wright's law or Moore's law to try and predict the future behavior of a technology. Actually, Moore's law has been used for a long time to predict where computers are going to be at a given point in time reasonably well, I would say. But we set out to understand how good these predictions are, because if you go back to the example I gave of solar energy versus alternatives, it's really critical to know whether the forecast is any good. For one thing, the skeptic can say, well, how do you know it's not going to just turn around? If you're, say, arguing, as I would, that we should actually invest more in solar energy rather than nuclear power, precisely because it's going to improve, and the more we invest in it, the more we drive the cost down, and so we can actually speed our progress towards cheap green energy by actively engaging in this technology. The skeptic would say, how do you know that's not going to be true? How do you know that the extrapolation that I'm making in that earlier plot isn't just going to turn around and go another direction? So we worked pretty hard on that. We collected data on about 50 different technologies. We tried forecasting these technologies, and I'll show you an example of using the central limit theorem to allow us to get error bars. And so what we did is we, first of all, pretend to be at some given time in the past. We forecast each future date from that point in time as if we didn't know anything about the future, didn't have any information from the future. We repeat that for all past dates. We score the different methods for forecasting based on their forecast errors. So we get experience with how good our forecasts are in doing that kind of exercise. And now we pool the experience from different technologies by assuming the improvement process has the same form for all technologies. It just has different parameters. And so let me now elaborate on that. If we use Moore's law, we actually embed Moore's law in a noisy world by making a model like this. There are actually several options for what you could do here. But we say that the change in the logarithm of the cost, so if y is now the logarithm of the cost at time t plus 1 versus time t, that is how much does the cost drop in the next period, it's equal to some drift term, which is the average exponential trend, plus some scale that says how noisy this particular process is. So these are technology-specific constants, times some, scale 1 noise process. And it turns out Wright's law can also be written in a similar way, where now you've got some cumulative production variable that's driving the improvement process. Now, so what do? We fit all these to the data. We fit different parameters for each data set. But then, in order to get a feeling for whether our hypothesis about the errors is working, we use the law of large numbers to renormalize the distribution. And the result you can learn in an elementary textbook, it's a student distribution. And then we can actually use the forecast for one technology to test how good our forecasts are for technologies in general. And so in particular, we proved some results about how much these forecast errors degrade in time. If we look at a normalized measure of the forecast error, here we're normalizing by how noisy this particular technology is, and we look at the squared error, then we get a formula that depends on the number of data points m that we have times tau, where tau is the horizon into the future that we're forecasting, plus tau squared over m. And this formula intuitively comes from the fact that this first term is a diffusive term. If you knew the parameters of this process perfectly, you'd have some error just because the noise is diffusive. We've assumed a random walk with drift. Plus a term here that depends on the error that you make in fitting the parameters, which when you have a lot of data to fit, this term starts out being smaller, but as tau gets bigger, this term is always the one that dominates. So your uncertainty in your model always dominates asymptotically as you try and make a long-term forecast. So we can then look at how our theory, which is shown here in a solid line, fits against the data, which is shown here in dots, where we've collapsed our data from forecasting all the 50 different technologies onto different horizons, taking into account the fact that we can forecast some technologies better than others, and some technologies have different improvement rates than others. And it turns out, though, I should say, that in order to get this model, we actually had to generalize the random walk with drift to allow for autocorrelation. The model without any autocorrelation gives this curve here. With autocorrelation, we get something that scales the same way, it just has higher overall errors. And so we can collapse onto the student distribution. This is the hypothesis that we end up with, that there's some factor. We could take any forecast at any time horizon and collapse all of our 6,000 forecasts, or however many, almost 6,000 forecasts, onto the student distribution. And we see that, in particular, once we take into account this autocorrelation, we get a collapse that we cannot reject statistically. So the theory works surprisingly well, and at the end of that, what do we have? We can take a time series like this, fit a line to it like that, and we can make a forecast now where we have probabilistic error bars. That is, we can say there's a 1 sigma chance of being inside this black area and a 2 sigma chance of being inside this gray area. So there is actually some chance, based on our experience, if this is all we have to make a forecast, it's much more likely to go down, but there's maybe a 5% chance that there's no progress in the next 20 or 25 years. So we now know how good a bet is it to put our money into solar energy, and how much improvement do we expect to get? And the answer, by the way, is that it's very likely that by about 2025, solar energy should be cheaper than coal, and by 2050, it should be significantly cheaper than coal. Let me just remind you that we have this distribution, but maybe I'll close this part of the talk by mentioning that, you know, there's been, if you read the literature on climate mitigation, I've been frustrated for decades now at the complete pessimism about the possibilities for what renewable energy can do. One of the arguments that's often made is such a tiny fraction. You know, it's only 1% of our energy right now. There's no way we can ramp up to having it be a significant contributor in the timescale allotted. But if you just take the data and extrapolate it, so this actually comes, believe it or not, from BP, an oil company, and so you look at this is the overall amount of energy that we spend. So up till here it's history, and beyond that it's an extrapolation. And you look at the different sources in producing that energy, you can see, okay, most of it's still fossil fuel, but this green curve here is solar energy. And so this is, it's expanding at a rate of about 45% per year at a fairly steady exponential rate, although with a little hump back here in the 80s. And the crossover point where it could generate 20% of primary energy is 2027. Now, I chose 20% as my point because above that, we really have to start thinking about storage. Without storage, more than 20% contribution is not realistic. But that's a pretty major contribution, and in contrast, the IEA, which is the leading international group that talks about these kind of things, says PV will generate 16% of electricity by 2050. That's actually a much more optimistic. They used to say 11%, and they recently upgraded their estimate. And if you look at their estimates, you can see they've been consistently wrong, consistently off by a very large factor, always way too pessimistic. One wonders, I mean, I think their experts just don't believe in extrapolating the curves. Now, let me just point out that the results I presented you were for Moore's law. You can actually do something similar with Wright's law. We're wrapping up the paper in that. That has important policy implications because it means we can actually accelerate things by pushing them down the curve faster. And it's very important that some technologies are better than others, and we can compare them. But I want to get on to the second part because I'm worried I'm running out of time. So now I want to present an ecological approach to understanding growth. And you know, ecosystems are an interesting thing. I actually have two different theories. I have a theory of ecosystems in financial markets in this paper here. But I'm going to talk today about an ecological theory for production networks in the economy. I'm increasingly convinced that ecology is a much more general thing than biologists realize. They're just the first ones to embrace it and understand how important it is. The internet, by the PageRank, for example, is very much, as I'll show you, it's parallel to a key ecological measure. Now, the framework we're working in here goes back to the work of Vasily Leontiev between the Great Wars. He was a Soviet defector who ended up at Harvard. In his formalism, nodes are industries, so it's a network model for production. Nodes are industries, each producing a good, and there are weighted directed links, which are the inputs for each industry. So the economy is a network that takes in input goods, transforms them through some kind of production process that produces output goods, which may either be consumed or may provide inputs for other production processes. And you can cast this in terms of physical flows, where the units at each link are widgets that are flowing, or you can cast it in monetary terms where the units are dollars. There's a precise analogy to equilibrium chemical kinetics. In fact, You can use the same kind of ideas to write differential equations that look just like kinetic equations in chemistry, the only difference being these stoichiometric parameters aren't integers necessarily anymore. And then, you set dx dt to 0, and you get the Leontief equations, which then become algebraic equations. And the key observations are based on conservation laws. Like, in this equilibrium, the money flowing into a node is equal to money flowing out of the node. And in the national accounting statistics that were cooked up, inspired by Leontief, and that now are important parts of national planning, the accounting is effectively rigged up to create a conservation law. I mean, accounting is essentially all about, from a physicist's point of view, it's just how do we rig things so we get a conservation law. Just as in physics, we basically, at first energy wasn't conserved, but we kept adding terms till we finally got it to be conserved. Okay, now, so the point I want to make today is that the structure of the economy, the trophic structure of the economy, matters for growth. And to see the idea, compare a flat economy where we have a final goods sector here, that's consumption, and we have two production sectors that are both in parallel, but it's a simple one-step process. You could imagine an island where we just pick coconuts. Now, consider instead a chain economy where there's a final sector, where one sector produces an intermediate good that's then used by another sector to produce the final good. And now, suppose you consider what happens if these guys in these sectors are working equally hard to make improvements. How will those improvements be felt in the economy as a whole? Well, here if there's an improvement, that's just passed to the final sector, 1-to-1. But here, if these guys make an improvement in sector S1 in their intermediate good, and it's passed to S2, and the guys in S2 make another improvement, you now get a multiplicative amplification of the improvements, and if they're all improving at the same rate, you end up with a faster improvement rate in the second case. Now, so then what we've done is work to make a theory that gets at this idea and allows us to apply it to a general economy. And so we assume a simple local process for technological improvement. We see how this improvement's amplified as it propagates through the economy, and we predict that all else equal, the rate of growth is going to be proportional to the aggregate output multiplier of the economy, which is just what economists call the trophic depth of the economy. How deep is the food chain? So, and I should say this, we can actually write down, there's a precise analogy between food chains and food webs that you think about in ecology and economic production, where the only thing that really changed, I mean, there's a few little details that change and the names change. I mean, economists have thought about this, but not in these terms. And the basic idea that I'm giving you here is one that has been missed by economists up till now. Now, in our theory, and let me just say, we're actually using Leontief's formalism in a bit of a different way than it was used originally. This formalism was used, for example, by the Soviets and by the Cubans for centralized planning. They'd say, you know, we need better agriculture. We need tractors for better agriculture. So they would figure out what sectors they had to grow in tandem in order to produce the things they needed to produce, and calculate how many tractors, how much fertilizer had to go into making the improvements they needed in the agricultural economy. We're using it in a different way, so in a more evolutionary way in some sense, in a weak sense. So we assume that, okay, design improvement can happen through lots of things. You can change the inputs, you can substitute one thing for another, you can create new goods and grow the network, you can improve the social technologies of production and distribution, you can increase the combinatorial possibilities so you have a better palette to design new things. All these things are important. We're going to just make a very simple theory focusing on this first one. And so in the Leontief formalism, we can write down some algebraic equations where x is a vector of the quantities of the goods that are produced, p is some vector of prices corresponding to each good, capital P is a matrix of those prices with those prices along the diagonal, phi is a matrix of the normalized physical flows of these goods through the economy, and A is the normalized monetary flows. So A is actually a stochastic matrix where its rows sum to 1, so that you can think about a dollar as being, in that sense, a conserved quantity as it propagates through the network. So in our model, we assume that design improvement corresponds to an overall decrease in the material inputs to perform a given function. So we look at this matrix phi ij for, in other words, to produce good I, we have an input good j, and we assume that the amount of that good we need, of all these goods we need, is going down proportional to some factor that's specific to good I, and times some factor phi ij. So we just postulate that equation, and then we turn the crank within the Leontief formalism to see what happens. So here are these equations back again, and we differentiate them. So we can, for example, differentiate the price vector and get an equation that looks like this. And then we convert back into monetary terms. Why? Because that gives us universal units. Phi, we need to be in phi units in the phi world of physical stuff first, because we have to make a postulate about the physical process changing, but then we can calculate its monetary consequences, and we do that because that's where the data is. It's impossible to get data about the physical goods themselves. Now when we do that, turn some crank, we get some predictions that prices go down according to some factor like this that turns out to essentially involve cap centrality, so going back to PageRank and measures like that. So we take the identity matrix minus this money flow, the transpose of the money flow matrix, we invert it in what's called the Leontief inverse, and then we evaluate it against this vector of improvement rates in each industry, and we get a vector of the rate at which the prices drop in each industry. And similarly, we do a little more, and we get the GDP growth of a country, a closed economy, is roughly the same expression times some vector that's just telling us the share of the different industries in the economy. So this is effectively averaging the growth rates of the industries in the economy. And so we now have a prediction. And we can test it. We test it against empirical data by applying it to data from the World Input-Output Database on 40 countries and 35 industries over about 15 years. And first of all, we see that we get a heavy tail distribution of these improvement rates. So these are the improvement rates for a given industry in a given country in a given year. And the improvement rates are ranging from minus 60%, meaning things went dramatically backwards, to 60% over here with a slight, we should actually probably draw a little line here, there's a slight, the mean is slightly positive at around 2%, reflecting the growth rate, average growth rate of the world economy. And but we see it's a very noisy process from this figure. And by the way, I should say that what these dots represent is the growth attributable to that industry in that country in that year by itself, taking into account all the improvements that it inherited from other industries and factoring those out. So you can really say how much did that industry improve by itself. Now, the other key thing I should say we were able to prove doing this that also surprisingly hadn't been, actually an economist had noted that empirically this seemed to be true. We were able to prove it. We can show that the average output multiplier of the economy, that is the trophic depth of the economy, can be reduced to the gross output over the net output. That is, the gross output is taking into account the production of all the intermediate goods. The net output is just the final goods. And so basically, the more intermediate goods you're producing, the higher the trophic depth in that economy, and according to us, the faster that economy should grow, all else equal. Now, and we, by the way, can prove that's an invariant under aggregation providing the accounting is done right and we can define what doing it right means. So that is, you need to actually properly take into account the internal processes of companies in order to make sure the intermediate goods are properly logged. And by the way, we actually can test this. This is some US data, and you can see that even when whether we use a 6-digit classification of the input-output matrix, or a 1-digit or 0-digit, by just taking the gross output over the net output, we get an almost constant curve, illustrating that the result's pretty good. Now, okay, finally, we can show that the returns that an industry will get are going to be, the rate at which an industry should drop is proportional to its trophic level, and the rate at which a country's GDP should improve is proportional to sort of the average improvement rate of its industries times their average, times the average trophic depth of the economy. This would be true if this was a closed economy. There's some problems because the real world, of course, individual countries, the economies aren't closed. But nonetheless, it's first of all useful, I think, conceptually to look at things this way. So here we see the economy of China, where we plot the trophic level of the industries, measured the way I've been talking about it here, arranging the industries in a standard classification where we have agriculture over here, manufacturing here, and services here, and where we plot green arrows if the input of an industry is above a threshold. So for example, agriculture is an input to the food industry, so we plot a green arrow and it's above the threshold that we chose. And you can see in the the size of the circle is the size of the industry in the Chinese economy. And you can see in the Chinese economy, well, first of all, the trophic depth's pretty deep. Of the industry with the highest trophic level is transportation, with 5.4. This is like electricity and optical manufacture, very big one. Rubber, chemistry, okay, I always get these, manufacturing. Interestingly, agriculture is the lowest one that I'm plotting here. We've left out households, which by definition have a trophic level of 1. And I should say, actually, that the trophic level turns out to correspond to the average, the mean path length for $1 to reach the household sector. That is, the trophic level of an industry in this picture is if that industry, if you look at the dollars that industry spends, or the, I'm now forgetting what the Chinese currency is. You guys, what? It's the yen? Yuan. Okay. So if a yuan is spent in that industry, how many steps before it gets back to being paid to somebody as a worker? And you can see it takes more steps in the Chinese economy than it does in the US economy. But to finish what I was saying, agriculture is quite low, and you see this kind of shape here. Now look at the US economy. So first of all, the overall level is much shallower. The US economy is not as deep. And furthermore, the industries that have big weights are much more down here in services. The industry, the biggest industry with a high level is actually real estate. Here's transportation, which is still high. The highest trophic level industry is this one, COK, which is nuclear and fossil fuels. So that's the industry with the highest trophic level in the United States. Interestingly, though, agriculture is now one of the higher trophic level industries, which is maybe, and it's actually, well, it's higher, and maybe that's just reflecting that agriculture in the United States is a highly mechanized, automated industry, whereas agriculture in China is still straddling a feudal society. So, okay, I think these plots give a little insight into how the economies function. Now, do they tell us anything useful about growth? So what we do here is we take the growth rate of GDP per capita for the 40 countries that we have in the World Input-Output Database, and we plot the average trophic depth of the economy of those countries on the x-axis. And so you see the scatter plot. China's up here. It's got by far the highest trophic depth and the highest growth rate. Slovakia, Turkey, Bulgaria, interestingly, we didn't expect this at all, have high trophic levels, and, well, you can see how good the scatter plot is. And all of the wealthy countries are down in here. So they're relatively low trophic levels, typically around 2.5, and relatively low growth rates. Now, of course, I want to stress that this isn't the only factor at work, and there's a lot of scatter here. It's not a great plot, but you have to look at this plot by the standards of growth economics, where all of the predictions have a lot of scatter. And, you know, we get an R squared of 0.38 and a p-value of 2 times 10 to the minus 5. So it does seem to be a real effect. It turns out, by the way, that there's another effect that when you look back at our original equation, in this equation, it turns out that there's another effect that, for some reason, that has nothing to do with our theory, countries with higher trophic levels, trophic depths, also tend to have higher growth rates. So that's independent of the effect that you get. I mean, in this regression, we effectively just assume they all had the same growth rate, but there's another effect going on that is the ones with higher trophic levels also have higher improvement rates. Now, so we've also tested this against standard growth models, and what we see is that this factor actually explains more than any of the other factors in standard growth models, and it remains statistically significant when you include it with the other growth models. So, okay, there's a plot of trophic depth versus GDP. You can see the cluster of developed countries up here. So they all have a similarly low trophic, but for some reason, having a low trophic level is not sufficient to give you a high, or to make you wealthy, but it does seem to be correlated with growth. These are a time series of these trophic depths through time. And now this is a plot that my graduate student Charles Savoie made, where he's plotted the trophic depth of the US economy as a function through historical time. So we've got the average GDP per capita of the United States on this axis, and we've got the trophic depth on this axis, and then he has tried to infer in this curve here what the this was through time. I have to say, earlier than 1950, it starts to get pretty speculative. Up until 1950, or since 1950, we have pretty good data. So I don't know how much we believe this part, but this part's pretty good, and you can see how the trophic depth of the US has dropped substantially since 1950. And if Charles is right, it actually grew until about 1900, peaked, and then has been dropping since then. Now, key points I'm making here. To explain economic growth, we need to understand technologies and their networked interactions with each other. Technological progress seems to have a predictable component, and we can know how good those predictions are. I think we actually could make much better predictions than the simple methods I've made here, but to do that, we'd have to understand things better. Growth's an evolutionary process, and I think biological analogies can be useful. And I want to end the talk by just mentioning that, going back up to a high level again, the economy, the technological ecology is extremely autopoietic in the sense that it regenerates and maintains itself, and it would be extremely difficult to reboot. If you imagine a science fiction scenario, there's actually a book, Canticle of Leibowitz, that a little bit gets at this. Imagine that all technology was for some reason wiped out. And imagine that there was some set of monks that had a library that actually contained all the books that would tell them how things work. And even to make it easy, let's assume they had 100 years of freeze-dried food. So all they had to do was work to try and get things going again. If you start thinking about what the steps they would have to take to get the amazing engine that produces all the stuff that we had going again, priming that pump is an enormously difficult task, because you have to you have to figure out how to smelt metals and build some simple tools, and then that makes it easier to smelt the metals better, and going around that circle, you have to go around that circle again and again, reproducing progress, even if you actually knew what it was you were trying to do. And of course, in reality, and really what technological growth and economic growth are about, is a process in which we're both doing that process and we're discovering new things at the same time through this process of tinkering. Now, I mean, I'm interested in this because I believe there exists an evolutionary theory for technological change that could really provide us with key insights about the nature of technological innovation, and such a theory would combine elements of economics, biology, engineering, and physics. We're a long way from that theory, as I think the primitive efforts that I presented today illustrate, but I do think that theory is lurking out there. And you know, I've made a few attempts to get grants to start trying to play Linnaeus and get a proper classification of technologies, and you know, I think we're seeing hints of more non-equilibrium theories that allow us to think about economic change in a way that respects the ecological and evolutionary nature of that process, but it's a field that's completely in its infancy. And so with that, I'll end my lecture. Thanks.
Thank you very much for a fascinating lecture. Are there questions?
So you showed a lot of graphs which are all showing quite straight lines. But let's say if you take an invention like in biology, like you mentioned also sequencing, it looks to me that those things are going really in steps. Like, for instance, you have Sanger sequencing invented, and then for 10 years nothing happens almost. I mean, it goes extremely slow, and suddenly you have the second generation sequencing.
Yeah.
And now, a year ago, you have this nanopore technology. It goes like suddenly quick and then slow for a long time.
Yeah. Well, I think, excuse me, even for photovoltaics, you see some kinks. I mean, a lot depends on the way you plot the data. I'll actually go to a later plot where you can see a bit. Yeah, this plot here is a plot of just, not the entire photo, but even here what you see is you get this plateau, and then there's a sudden drop. And if you start digging in, you see that there's a story here. Well, what happened? There were material shortages and things happening here. Around here, the Chinese started getting involved, and then they put a lot of competitive pressure, which actually coincided with a lot of support from the Germans. And so there's a complicated story behind every bump. And I don't want to argue these things are smooth. And I don't even, I mean, to be honest, we were a bit shocked that we could get, to go back a few equations, I mean, this equation is sort of disturbingly simple, particularly because we ended up putting in Gaussian noise for this. Now, you know, there is this autocorrelation that I didn't put in because I didn't want to write down complicated formulas. And the autocorrelation actually gives you more excursions and makes the ride bumpier. But you know, we looked for long memory processes. We didn't see much evidence for long memory processes. Now, that said, we don't have very good data. And we looked for power laws. Maybe there's a lot of big jumps, but actually we didn't see, power laws didn't seem to make that big a difference. So I agree with you that there are these jumps, but the surprising thing is, despite it, this kind of random walk with drift is good enough to give you a reasonable...
It could also be that those, let's say, plateaus you see, that they're also because many technologies, they co-evolve and they come together, and suddenly at that crosses, then you see the big spurts going on. Could you predict those if you take more technologies together in your prediction? Now you take them one by one, but in fact, they are connected in some way.
Yeah. Well, you know, I agree with what you said. I heard once a talk by a chip designer who talked about Moore's Law and said, you know, you guys just think Moore's Law is something that just happens. It just somehow magically takes place. But to us chip designers, you know, we're going along and we're stuck. We don't know how we're going to make the next improvement. We sort of believe it must be out there, and our back's against the wall, and then suddenly somebody has a great idea, and we break through, and he was pointing out, actually, it's bumpier than you think. But still, when you stand back and look at it over a 50-year period, it starts to look pretty smooth. You can actually make curves for the progress of computers that go back 150 years, going back to mechanical calculators. And they also look surprisingly smooth, although they start to look super exponential when you look at those. So the exponential hypothesis may be a local hypothesis because we're only looking at periods of 40 or 50 years.
I have mathematical questions, but I don't want to state them now, but more on the higher level. What I find very fascinating is this analogy between evolution and nature and technological evolution, and we have these periods of extreme productivity in creative ideas and both. There's a Cambrian explosion, for instance, and there is a Renaissance. And there were other periods, like the years 30s in the US.
The Industrial Revolution is
Yes.
the most famous in technology.
So thousands of new creatures came up in technology.
Yeah.
Do you see a parallel? What is the role of diversity here?
Well, I think diversity plays a big role. It's unfortunately hard to get the data to convincingly quantify what's going on, but you know, if you think about it, if you just ask a question like how many SKUs are there? SKU is a zebra stripe, which means that you can swipe something there's millions of SKUs now. And you know, unfortunately, the guys that keep track of this data are constantly reusing them and so on, and don't have a very coherent, for us evolutionary guys, we have not been able to get a good data set on what's going on. But the palette of technologies that we have to work with has grown enormously through time. Now, that said, you can also see in this book by George Basale, he points out that there were 500 types of hammers being used in Britain in the time of Karl Marx. And he shows this picture of all the different kinds of hammers, because back when people were pounding on things a lot, they would make very specialized hammers. A lot of those hammers are probably extinct now. Nonetheless, I think there's a very strong trend from those apes you saw in my second slide, who were using, you know, their technological toolkit was very simple. They basically had some scrapers and chippers, just a couple of things. That toolkit has evolved enormously to have the toolkit that we have now. But, so I think diversity is key, and you know, you see it even in my lifetime. I mean, I actually built the first wearable computer, as it turns out, in 1978. Actually, no, 77. I built it in 77. It didn't really work till 78. But you know, that was a major breakthrough, because by having a microprocessor, you suddenly, the toolkit, the palette of the things you could do in a simple way with an electrical device relative to the previous era where you had discrete logic, it was just a complete game change. And as an example of, you know, as we find the right building blocks, our capabilities become enormously expanded.
And the cultural climate, is this important?
I mean, it's very important, and I think, let me say that there is a whole field of people in sociology and business schools who study what is it about a particular social process that causes technology to take off. Why did Silicon Valley occur around Palo Alto and not in Boston? And those are very important questions, but I think the biological component is missing, because I think there's some broader roles, like, well, getting clear explanations of Moore's law and Wright's law. We actually still don't have those. And understanding, in the more the way evolutionary biologists use evolutionary theory, that's still missing. And so that's the part I want to put in. I think that part can work together with the more social process story.
There was this Lake Victoria, and also in very short time many different species evolved there.
Yeah.
And so I think these are kind of, maybe we can see some analogy between.
Yeah, yeah,
but
yeah.
That's I find it. Okay, thank you.
Sure.
Are there more questions?
Open source, Singularity, Rifkin, this popular trends that you can read and listen lately sort of triggered me to your explanations of the Wright law and then the decrease of the cost. So I'm trying to get thing in my head. So how do you, I mean, in the future, if things are going like development is going fast, new things are coming up, digital manufacturing is coming, the cost is getting less and less. So is it possible that we could have marginal economy what Rifkin is, I think, talking.
Yeah.
If we don't.
Well, so that's a good question. I think it's certainly possible. And, you know, there was already in the 60s, maybe this was the 70s, I'm not sure, it was the 70s, there was a study of whether it would be possible to build self-reproducing aluminum mining modules on the moon. So we would send up a rocket with a little robot,
Yeah.
and the robots would crawl out, and they would start collecting aluminum, and they would make more robots, and then at some point they would start, I don't know what they would do with the aluminum. Maybe they would build a space station orbiting the moon or something. But, you know, these guys decided, yeah, it probably could be done. And in a sense, when we talk about having the marginal economy where the robots make everything for us, we're talking about a certain version of that. It's just that we rely on them to give us stuff they're making. And we try and keep control of their reproduction. And we guide it and maybe design it ourselves. But I think those scenarios are quite plausible and quite sobering to think about. And maybe to go back to Teilhard de Chardin, or another name to mention would be Olaf Stapleton, who wrote a book called Last and Future Men, which is a sort of history of the future, where he envisions the combination of genetic engineering and cybernetic engineering, creating, you know, intelligent beings, and humanity evolving into something quite different than what it is now. And I don't think these ideas are implausible. I think the time scales may be still a bit long, but I don't think it's at all implausible. In fact, to be honest, I think it's likely. And so...
Okay, yeah. But then we again limit that there is again your colleague physicist who in MIT published that limit of growth. We have limited resources, so I was going to be pull out.
Well, so I think there's another. You're thinking of Dennis Meadows.
Yeah.
So yeah, we certainly have limited growth, and I haven't mentioned the sustainability component of this here. In order to have a sustainable growing economy, we have to dematerialize GDP. And interestingly, there has been a trend of dematerialization of GDP. GDP, if you look at how much does $1 of GDP weigh, that weight has been going down through time, even once you adjust for inflation. And, you know, it's partly things like, you know, this. We have these lightweight technologies that cost a lot, and but it's pretty slow. It's less than 1% per year. And whereas our growth is faster than that, and particularly if people in developing countries are going to achieve similar levels of growth, we're going to have to dramatically dematerialize GDP. And I think it's possible to do that, so that in the future, the growth we'll have things that are smarter, that arrange information better, that are of higher quality. You know, you think about the difference between seeing a play seeing some crappy movie on TV versus a really well-performed play. GDP will change. I think we will still have growth.
Okay, let's have the last two questions because it's getting a little bit late.
Yeah.
Let's Roland, your question.
Do you think that tool use and technology is uniquely human, or is there a continuum between tool use and animals, or even things like termites mount building and things like that?
Yeah. So there's there's now a whole library of amazing examples of animals using tools. But when you look at it, it's all still at a pretty simple level. You know, a bird will put a straw in his beak and use it to pry something out, or they'll use a stick, or either to crush something or pry it, or pretty much. So I think on one hand, I think it's very cool that animals do that, but it's a quantum difference. I mean, it's a gigantic difference from the way humans use tools. And I think we are specifically animals that evolved to use tools, and that has turned into our fondness for technology and altering our world with our technology and completely taking over our environment.
I mean, but a termite alters the world as well.
No, they alter, and this goes along with niche creation and biology.
Yeah.
It's just that I think we do it on steroids and in process that's very fast compared, I mean, termite nests 100,000 years ago were probably pretty similar to what they are now. Human societies, you know, has changed radically in that period.
Okay, final question.
You mentioned the need for a better taxonomy of technology.
Yeah.
How the patent office taxonomy is the best we have, but not good enough. Do you have any suggestions on how to come in the immediate future to a better taxonomy of technology?
Yeah, I do. I've written grant proposals. I wish you were a funding agent, because I haven't had any success. But yeah, I think, first of all, patents, there's 10 million patents in the American, or 9 million patents in the American patent database. And those, we don't have a record of all of them, but we have a record of maybe half of them. And so we actually have the text of the patent. We have a rich classification scheme that the Patent Office has built up. And there's a lot of information there. We have a citation record of what patents, other patents cite. We have Wikipedia now, which is an amazing record of stuff. You know, Google Ngrams, there's a lot of data that we could use. But at the same time I say this, it's a hard problem. So I'm actually trying to put together a team that would involve some people who are really good at things like web scraping and textual data analysis on one side, with people who are good at things like cladistics that the biologists use on the other side. So I'm actually writing another grant proposal right now with a team I'm trying to assemble to try and do this. And the goal would be a taxonomy of purpose, functionalities. So.
The very last question.
No, just a remark. You are now in the town where Linne wrote his book. Maybe
Yeah,
this
that's
inspires you.
Okay, that's a very good way to end.
That is an excellent way to end. Thank you.
Okay, let's thank Professor Farmer once more. And there will be time to ask questions, but more.
Right. Great.